This is Jon Zhang. It's my great pleasure to have this opportunity to give a presentation in this webinar. Since PowerAmerica is not
satisfied with to send your message with normal delivery, press 1. To send your message with urgent delivery, press 2.
I'm trying to mute whoever that is. Please mute yourself if
Are you still there? To send your message with normal delivery.
So it's connected.
Okay, I found them. Please continue.
Okay, I'm sorry for the interruption. Since PowerAmerica is not conducting technical project, I would like to take this opportunity to give you an overview on the wide-bandgap devices, current standards, and future perspectives. We'll start with the marketing position of the wide-bandgap devices, namely silicon carbide and the gallium nitride devices. Then we'll review the current standards of both devices respectively. Since the cost seems to be a major barrier for wide-bandgap devices to penetrate the market, so we will compare the cost of the current wide-bandgap devices in the market to the conventional silicon counterpart, and see the way approaches to reduce the cost for the future. Now we summarize the talk with future perspectives of the devices development and applications. So this is a very well-known figure that shows the different applications for power devices from the low power such as laptop, motor drive, to high power like the wind applications and the TVs. And highlighted in the yellow box, you can find the applications for silicon carbide devices. You can see that the silicon carbide devices are mostly used. I'm sorry, in the high power applications, because the silicon carbide device right now the structure is a vertical device structure. It could achieve a large current levels potentially. On the contrary, the
just a second, John. There's something wrong with the WebEx.
It's not.
Yeah, somehow you're not showing. You're not in the meeting anymore.
What?
Yeah.
Okay.
You must have hit something.
Sorry about that. Yeah.
Give us a minute, please. Something, we had a little hiccup with WebEx. Oh, that's for audio.
Close?
No. Go to share, screen sharing.
This one?
No.
God.
Oh, okay. You are still there. Yeah, I'm sorry. Just open up the presentation again and maximize it. Okay, you sharing your screen?
Oh.
Go back to the WebEx app again. Go to share. My screen. There you go. Yeah, close that. Yeah. Okay, sorry about that. Please continue.
Sorry about that. And let's start over again. So if you take a look, this figure can show the different applications for power devices. Highlighted in the yellow are silicon carbide devices. You can see that silicon carbide devices are normally could find a good application areas in high power, high voltage applications such as the TV and wind applications. On the contrary, the gallium nitride devices, there is a good devices for low power, low voltage applications, because Okay, because the gallium nitride device normally is a lateral device. It has low capacitance compared to silicon carbide devices, so it has it could operate at a higher frequency for low power applications. You have conducted a few studies. It shows that silicon carbide device market is gradually ramping up. You can see that over a few years, the silicon carbide market could reach $1 billion US dollars. Right now, the major market for silicon carbide is there for the silicon carbide is the power supply and PV applications. But gradually, the EV and HEV market is catching up. It will be getting bigger over years. In fact, Tesla has announced that they have used silicon carbide MOSFET in their Model 3 inverters. So it's very promising for silicon carbide devices to be widely adopted in the market. Gallium nitride power device market is relatively smaller than silicon carbide market size, and but again, it's going to increase as well. The major application for gallium nitride devices are the power supplies, the chargers, so it's for the low power field, as you can see from this chart. PowerAmerica is very proud to support a few many projects with gallium nitride power devices. For example, the Navitas has developed a very compact USB laptop adapter with gallium nitride power ICs. This adapter could run 3 to 4 times faster with a much lower loss than the typical adapter designs. So that shows the advantages of gallium nitride devices in power applications for high frequency, high power applications. So right now, let's start to review the current status of the power devices. For silicon carbide devices, this figure shows the major players of the device makers. And for example, the Wolfspeed, Infineon, ROHM, and they are the top 3 manufacturers of the silicon carbide devices. X-axis shows the voltage rating from 600 volts to 60 volts, 900 volts, and 1200 volts for silicon carbide commercially available devices now. And they have different ratings, the green current ratings showing the y-axis. And both planar and trench structures have been developed and commercially available. Pretty much the US-based company, they're developing the planar structures, and the ROHM and Infineon, they're using the trench structure for their product. The higher voltage than the 700 volts is gradually developed and will be available in the market pretty soon. If you take a look at the planar structure, the left figure shows the very simplified cross-section of the device, and the MOS channel is fabricated on the silicon face. In the right figure shows all the devices so far have been demonstrated on silicon carbide. You can see that the silicon carbide devices have been developed from 900 volts to up to 15 kV. That figure was published in 2015. So there are low voltage coming. But from this figure, you can see that beyond 3.3 kV, the specific on resistance of all the silicon carbide devices are pretty much identical to the theoretical values because the drift resistance is dominant for these devices. When the bottom voltage is reduced, the channel resistance and the substrate resistance becomes dominant. So you can see that for the 900 volt devices, the on resistance still way higher than the theoretical calculation values predicted. So I just borrow the process flowchart from Dr. Song. Pre-process flow for silicon carbide devices start with alignment mark etched on silicon carbide. The right figure shows the wafer structure. It grows the N-type 8-layer silicon carbide on the silicon carbide substrate. After that, if you make a MOSFET, you need a few times of ion implantations to implant the P-wells, the source, and the GFX implantations. Normally, in this implantation, most of the process require high temperature implantation to reduce the crystal damage, and also all these implantations need to be activated at relatively high temperature. So that's a typical process for silicon carbide. After that, we do the gate oxidation, and also we knew this oxide with NO. So that's a very well developed process. You do the polysilicon gate, that's the typical silicon process, and make contact. For the contact, you can use nickel for N-type contact, aluminum-based metal for P-type. So some study has shown that you could use single metal for both contacts as well. You will use this contact at 900 or beyond temperature to make ohmic. Then you deposit the metal and protection. Normally, the backside needs to reduce to grind off to some thickness to reduce the resistance component from the substrate. And after that, use less anneal to make ohmic on the backside. So, majority of the process to make the silicon carbide MOSFET are identical to the silicon process, except the implantation, activation, gate oxidation. Some ohmic contact process for silicon carbide is different from the silicon. Last year, Wolfspeed has demonstrated low voltage devices at 50 watts. That chip used Gen 3 platform, and the cell pit was optimized for low resistance. And also, of course, for this low voltage devices, the drift layer doping is higher than the number used for high voltage devices. It has been optimized to reduce the resistance component from the drift layer. And also, from study have shown that the drift layer doping concentration largely affect the temperature coefficient of the resistance. The higher doping concentration of the drift layer, the lower temperature coefficient of the ion resistance. And also, the over-layer process was optimized and modified for soldering and other sintering process for module applications. And also the gate resistance was optimized too to reduce the switching oscillation. So overall, this device is designed for the traction inverter drive applications. So for that application, it requires high current rating. So that's why the resistance of this chip is low, 7 million. And also the chip could operate at 175 degree phase junction temperature, and also allow double-side cooling. This device could pass the automotive reliability qualifications. The results have been published in last year's ASCRIM. So that this figure shows the blocking characteristics of the devices. So the device process 60 volts, but actually the avalanche at 900 volts and beyond. So the temperature coefficient of the leakage current is very minimal. This figure shows the family curves of the devices. The gate bias, the operation voltage for the gate is 50 volts, and you could get a specific ion resistance of 6.5 at 25 degrees C, which represents 1.8 milliohms meter squared of specific ion resistance. If you calculate the resistance component, you can see that the majority of the resistance of the devices is from the channel at the room temperature at least. So at high temperature, the channel resistance will be reduced. So if you take a look, the resistance dependent on the temperature, you can see that at a lower temperature, the resistance increases with lower temperature because the channel resistance is getting higher. And when we increase the temperature beyond the room temperature of 50 degrees C, the temperature increases again because the drift resistance increased and channel resistance reduced at high temperature. But overall, if you compare the resistance at 150 degrees C and room temperature, is just increased by 15%. So the temperature coefficient of this device is very small compared to the high voltage devices, or let's say 1200 volts. Normally is 50%, 10 kV is even more. We compare this resistance dependent on the temperature with the 600 volts 17 milliohm silicon superjunction MOSFET, as shown in the right figure. You will see that for the silicon superjunction MOSFET, the temperature coefficient is very positive, and it's increased twice at 150 degrees C compared to the room temperature. And we also plot the silicon carbide MOSFET, the curve, to compare with the silicon. You can see that this silicon carbide device is pretty much flat coefficient, pretty flat over the temperature. And also the charge parameter has been measured and compared with the figure of merit of the product of the on-resistance and get charge. As shown in the right figure, you can see that at room temperature, the silicon carbide centrifugal devices is better than the silicon superjunction devices, and this number is getting even better at 150 degrees C. So this result has shown that silicon carbide MOSFET at 650 volts exhibit much lower figure merit of RDS1 times QG than silicon superjunction. I will show later actually the price. If you calculate the price of silicon carbide compared to the silicon, the price is not that off based on the study we have. One problem for the issue for the planar MOSFET is the low channel mobility. But you have to operate the devices at fairly higher gate electric field to fully turn on the device. So to solve that issue, people developed the trench MOSFET because the study has shown that the silicon carbide most channel mobility on the E phase is higher than the mobility on the silicon phase, as shown in the left figure. It shows the mobility versus the gate field at room temperature and high temperature for devices made on the E phase and the silicon phase. So you can see that the mobility on the E phase is higher than silicon phase, and also it has shown different temperature coefficient. And you compare the peak mobility depending on the temperature, shown in the right figure, you will see that the silicon phase mobility increase when the temperature increase, which agree with the Coulomb scattering mechanism. On the contrary, the E phase mobility reduced with temperature, and it shows kind of ideal Coulomb scattering mechanism. So they have different interface property. So and also that property affects the temperature coefficient. The two major MOSFET, trench MOSFET structure right now developed by different companies. The first structure is double trench with ROM. You can see that there are very deep pivot implantations around the polygate to protect the electric field, high field from the drain bias. Infineon use a symmetric channel to protect the corner, but both structure looks different, but the physics they are pretty much the same. So both of them use deep implant to shield the field from the drain bias. so they could effectively reduce the field in the oxide corner. Here show the Fermi curve from Infineon's trench MOSFET. The major advantage of trench MOSFET, based on what Infineon claims, is that the peak electric field on the gate, when you fully turn on the device, is reduced to less than 2 megavolts per centimeter, compared to 3 to 4 megavolts per centimeter on the planar devices. And this lower gate electric field could potentially improve the gate reliability. That's what I claimed. And also, this device shows high threshold voltage, as shown in the right figure, is 4 to 5 volts before the drain current starts to increase. Planar MOSFET, normally the threshold voltage is between 2 to 3 volts. Again, the major advantage is the lower field, gate oxide field on the trench MOSFET. So there have been some studies on the gate reliability, and I just showed a typical study reported in the last year PCIM. In these two figures compare the gate reliability between the silicon carbide trench MOSFET shown on the left and silicon IGBT shown on the right. So the x-axis shows the numbers of the voltage beyond the operational voltage on the gate. So x-axis is VG minus VG use. VG use is normally the gate voltage device to operate when you fully turn on the device. So, and the y-axis is the failure numbers of 100 devices, is the sample size they used. So test procedure is just increase the gate voltage from the nominal gate device, VG use, and gradually increase to the gate rupture or shown gate leakage current from the stress. You can see that both devices show the extrinsic failures, showing the red bars, when you increase the voltage to some number. For silicon carbide, the VG minus VG use is around beyond 20 volts. On the silicon IGBT is beyond 30 volts. So their difference is maybe from attribute to the different gate oxide thickness. And both devices show the intrinsic resonant voltage at some number. It looks like that silicon carbide trench MOSFET has a higher failure rate, but generally speaking that silicon carbide trench MOSFET shows a comparable extrinsic failure rate than that of silicon IGBT. So it's very promising and shows the evidence of the gate reliability with the trench structure on the silicon carbide MOSFET. Further, in this Weibull plot, you compare the devices with thin gate oxide used in the planar MOSFET and trench MOSFET, which has a thicker gate oxide thickness. And you see that they show 4 manufacturers. Actually, there are 3. M1 and M2, I think they are the same manufacturer. M1 has shown higher failure rate because these devices will not get properly screened, so it shows higher early failure rate. If you apply a proper screening approach on this MOSFET, the early failure rate will significantly reduce, as shown in green or the yellow. Overall, for the planar MOSFET and trench MOSFET, they show similar early failure distributions. This the hum showing so they have a similar failure rate. The only difference is that the thick oxide fail at high voltage because the trench MOSFET had just because of thicker gate oxide. Both devices, they could meet the 20 years of safe operation criteria, as shown in this figure. One phenomena have been shown from the trench MOSFET studies is that the trench MOSFET interface has a high density of the broader path. So this trap could cause a substrate voltage, some hysteresis, as shown in the left figure. So when you hold the gate bias in the negative voltage for a while and sweep the drain current from a negative voltage to the positive gate bias, upsweep the device and get the transfer curve, you will see that there's a secondary hump shown up in the transfer curve. But this secondary hump will disappear when you apply a positive gate bias, hold there and sweep back, so it go back to normal. So the reason behind study has shown that because the interface, not interface, the AFES MOS interface has higher border traps in the mid gap of the silicon carbide diagram, and on the contrary, the AFES silicon carbide interface has higher interface in the near the conduction band edge. So that's why the silicon FET has low mobility, but has much small the transfer curve hysteresis is very stable, and the AFES has much higher mobility, 2 to 3 times higher mobility, but has higher hysteresis. So, but again, this voltage shift is fully recovered by applying a gate bias. But still need some studies for long-term certain voltage reliability on the trench MOSFET. And also in the future, the customer may want to reduce the gate bias further. So it's always desirable to reduce or to eliminate this effect on the silicon, so on the AFES trench MOSFET device structures. So in summary, the challenges in the power devices on silicon carbide for planar definitely we need high channel mobility, and high channel mobility could reduce the chip size further, and also could reduce the peak gate of red field. That's the most motivation to have the high channel mobility, and also that will improve the switching performance as well. Planar MOSFET also need to increase the threshold voltage to 4 or 5 volts from 2 to 3 volts. Right now we have the trench MOSFET threshold voltage stability needs to be further studied for long-term reliability concerns, and also some technology needs to develop for the trench corner protection. So that's the order for the challenges for the power devices. And let's start gallium nitride devices. Again, this chart shows the major manufacturer of gallium nitride devices. As you can see that most of the gallium nitride power devices, they are under 300 volts. And all the structures, they use the nominal of EHAMT structure. So there are a couple of structures with nominal of at high voltage, let's say 300 volts and beyond. Either use cascode configuration or use EHAMT configuration to achieve the nominal of high voltage block capability. That simplified cross-section shows the gallium nitride devices. They glue the gallium nitride in multiple layers on silicon substrate, and the 2D gas was formed between the argon and the GaN layers, source drain on the surface. The gate, they could use Schottky, and they could use the P-type argon layer or both. So to achieve nominal off performance feature of the gallium nitride devices. If you come over here, this figure shows the family curve of your gallium nitride 600 volts tank. You can see that the device shows the nominal off feature is block voltage and 0 gate bias. The body dial is the mean voltage of body dial is very small and also very fast because it is a unipolar device. And it has a better drain current generation behavior too. Only one aspect is improved for the gallium nitride EHAMT is the threshold voltage. This figure compares the different transfer curves among the GaN-HAMT and cathode gallium nitride HAMT, superjunction, and silicon carbide MOSFET, you can see that the E-mode gallium nitride has the lowest surge voltage compared to other devices. So for power applications, probably is desired to have higher surge voltage for the E-mode gallium nitride in the future. Another advantage of gallium nitride devices, if you compare with silicon superjunction, is that it has lower or with the similar resistance and similar block voltage. The gallium nitride devices exhibit lower capacitive values, and it has lower input capacitance and CUSS, and also the CGD or CRS show the pretty linear behavior compared to superjunction. And if you compare the total charge in the CUSS and energy stored in the CUSS, the gallium nitride shown in the red color here has lower values than the superjunction. So it indicates that gallium nitride devices could operate at an even higher temperature than the silicon counterpart, because the dead time could be reduced in some applications. This table compares the 650 volts power devices with different technologies: silicon superjunction, gallium nitride eHAMT, silicon carbide DMOSFET, and silicon carbide UMOSFET. And we compare some key parameters. For example, the surge voltage, the gate operation range, and all resistance at different temperature, the gate charge, the charge in the CUSS, and the reverse recovery charge, and also if the device has the avalanche capability. The number or the text highlighted in green means we are pretty much like this feature, and red means probably we want to improve this number or this aspect in the future development. So all these devices have similar on resistance at the room temperature. But you can see that silicon superjunction and gallium nitride eHAMT, the resistance increased significantly at 150 degrees. And DMOS and the UMOSFET on silicon carbide, they slightly increased at high temperature as shown before. But the advantage of the gallium nitride devices is has very small gate charge, and also there's no reverse recovery charge. So that's the advantage of the gallium nitride devices compared to the silicon superjunction or silicon carbide devices. All the silicon or silicon carbide devices are vertical devices, and it has a higher surge voltage or wider the gate operation range. So that's their desirable parameters for the applications. And also, in addition, they have avalanche capabilities. For some applications, it may be required. So, in summary, silicon-based devices has a superjunction at least, has a nonlinear CUSS and higher number, but is very reliable and cost is very low. Gallium nitride devices is lateral devices. Reliability needs to be further improved, and also probably we need to develop some devices, the gallium nitride devices with avalanche capability to reduce the cost in the future, but it has lower capacitors and it's no reverse recovery, easy to integrate for power IC. Silicon carbide devices, the major issue is high cost, and there's not so many software suppliers in the market so far now. But it's easier to scale for a high power, and it shows a lot of advantage for high power application, high temperature application. So all these devices could find their unique applications based on their advantage or benefit. Overall, I would say gallium nitride will pursue high frequency applications with small size, and silicon carbide, they want to pursue high power applications with larger chip size for module package applications as well. So let's compare the cost of the wide-bandgap devices to the silicon devices. This figure compares the gallium nitride pumped at a lower voltage, 30 to 60 volts, gallium nitride devices versus silicon MOSFET shown in the red. You will see that gallium nitride enhanced generally is more expensive than silicon MOSFET counterparts. But some current resistance value, for example, and they are less than 2 milliohm, and also some number with high resistance, at least based on the DGP numbers, the price is similar to the silicon MOSFET per unit. On the silicon carbide, if we compare the silicon carbide MOSFET with silicon superjunction and silicon IGBT, as shown in this figure, you will see that silicon carbide MOSFET, the price is very close to silicon superjunction at 60 volts to 800 volts range. But silicon carbide devices, MOSFET, are still more expensive than silicon IGBT, especially when the voltage rating is getting increased. So this table just compare the cost parity to the silicon IGBT. You see that the low voltage 2-3 times more expensive, and 1200 volts even higher. And there are many approaches to reduce the cost, to reduce the substrate or a layer cost, material cost, and to reduce the fabrication cost. PowerAmerica support projects to reduce the cost by the foundry service. This figure has been published for a few years from DOE. It's shown that how the cost reduced for 1200 volts 20 amp silicon carbide MOSFET from more than 50 cents per amp made in 100 millimeter wafers in a dedicated foundry with low volume, and gradually reduce if you could make the device with foundry with foundry work, and because this foundry work share the cost with the silicon devices, and also the cost is largely reduced when you increase make the device on a 150 millimeter wafer. But it's not that significant because the material cost is dominant. The cost could be further reduced when we use the families model with high volume manufacturing capacity in the foundry service. Rather, where PowerAmerica is supporting the program along this approach, but we're not there yet. From the device design point of view, always the smaller chip size always give you a better, will reduce the cost, apparently. So the one way to reduce the cost is by die shrinking. There are many ways to do that. I give you a very simple example, or a simple calculation on 1700 volts MOSFET. If I could optimize the drift resistance, how much I could reduce the chip size. Shown on the left figure shows the spectral orientation from the different components, from channel, drift, JFET, and spreading substrate. So the total spectral resistance at the room temperature on 1700 volt MOSFET demonstrates is 4.7 at the room temperature. When we increase the temperature 150 degrees C, the spectral resistance was increased to 8.7 milliohm centimeter square. And as you can see that the drift component is dominant for 1700 volts MOSFET, especially at high temperature. So if you could optimize the drift by subjunction, by some different new approach, you could reduce this component total resistance from 4.7 to 3 at the room temperature, and it's further reduced to 3.2 at high temperature. So it could potentially reduce the chip size by more than half. So that approach, it looks like very promising for high power silicon carbide devices in the future. And Professor Cooper's group has done some simulations on MOSFET with superjunction, as shown in the left side. That figure shows a very simplified the superjunction with N-pillar and P-pillar structures. And his simulation shows that if you design the pillar charge and spacing width properly, you could significantly reduce the drift resistance on the silicon carbide devices. So it shows at least the future development direction to go to reduce the total resistance. So in summary, for silicon carbide power devices, again for DMOSFET, we need to improve the channel mobility, 80 to 100 centimeters square per Vs. For trench MOSFETs, we need to significantly reduce the border traps to reduce the hysteresis in the transfer curve. And also for both devices, we need to reduce the cost by large wafer diameters and die shrinking, low material cost. For gallium nitride devices, probably we need to further improve the device reliability, and also we're going to develop the high voltage vertical gallium nitride devices or lateral gallium nitride devices, and also reduce the cost for high voltage devices. It looks like that the silicon carbide power devices, there's not much bottleneck for this. And the power electronics, they're ready to implement the silicon carbide devices in their system. For gallium nitride devices, probably we need some studies in the package and some modifications to develop some new passive parts like magnetic materials and capacitors, and also the integration of the power ICs for the future modules, gallium nitride. So that's it of my talk. Thank you very much.
Thank you very much, John. That was a really informative and information-packed presentation. So thanks very much for all of your work to put that together. So all of you, we have time for questions, so please, as I said, go to the WebEx box at the top of your screen, click on the chat function and type in your questions, and I'll read them out and answer them. John will answer them. So the first one is a general question. Will this video be posted anywhere afterwards? Yes, it will. If you accepted an invitation to the meeting, then you'll be sent a recording of the meeting automatically. If not, just shoot an email to me and I'll get it to you. Second question already is, how soon will 650 volt SiC devices can be affordable as 1200 volt devices? Number one. How soon will the 650 volt SiC devices be as affordable as 1200 volt devices?
I think it depends on the marketing demand, and also how much advantage for the silicon carbide devices could offer compared to silicon devices. In cost parity, we compare silicon devices, is shown previously, is not that much big difference from silicon superjunction. So the cost point of view does not look like a big issue for silicon carbide MOSFET. This is business decision, of course, but depends on the marketing demand out there.
Okay. The second question is, you mentioned GaN needs enhanced reliability. What is the reliability issue with GaN devices? Well, I'm not an expert in GaN, but based on what I learned or what I heard or from our communication, the GaN reliability frequently as the let's say XTRB, when you make the device commercially available. Right now, the gallium nitride devices, let's say you design for 6 volt applications, normally the blocking capability of the device is higher than 900 volt devices. So the reason behind that, for high voltage gallium nitride devices, it may have some reliability concern in the material growth techniques or the buffer layer quality.
So in addition to the surface passivation and the surface issues induced field clouding, so I would think the field reliability could be at least one major concern for the wide adoption of the gallium nitride power devices, especially for high voltage.
Okay, thank you. That's the end of the written questions, but a lot of people have dropped off, so I'm going to unmute everyone. So that's what I'll do. That's a little too noisy. I was going to try to allow everyone to just speak their questions, but obviously that won't work. So please use the chat function if you have any questions. We have a few minutes more before 1 p.m. Going once? Going twice? Okay. Thanks again, John. Thank you all very much for joining us today. If you have any follow-up questions and want to contact John directly, do you want to give out your email, or is that on the presentation screen any place where you can show?
Right. It's showing my first screen.
Can you go to the first slide so
Yeah.
everybody can see it?
Right.
There.
Yes.
Okay, this is John's contact information. If you have any more questions, please contact him directly, and he will be able to respond to you quickly with any answers to your questions. Can I have a copy of this presentation?
Sure.
Yeah, contact John directly, and he can email a copy to you directly. You're very welcome. All right, thank you all for joining us. Look forward to seeing you on the first Wednesday of October. Have a wonderful day.
Thank you, everyone. Have a good day.